Hi everyone, and welcome to Andes Hackathon, where innovation and collaboration come together. Over the course of this event, we'll tackle exciting challenges, push the boundaries of creativity, and build solutions related to AI. Whether you're an experienced developer or still in school, this hackathon will provide you with valuable opportunities to learn, grow, and gain new insights. For this hackathon, we're going to ask you to implement Softmax for neural networks. So what is Softmax? Softmax is a very common activation function for many networks including transformers, convolutional neural networks, and recurrent neural networks. Your challenge will be to implement the Softmax function on an Andes RISC-V vector processor while optimizing for accuracy and performance. We'll also provide you with several documents and materials in order to help you use our custom tools and gain a better understanding of the Softmax function, which can be seen here. If you want to request a cloud environment for the hackathon, please fill out the form seen here on the screen. If requested, you'll be provided a cloud environment with the following items, and you may use any optimization techniques that you wish, such as vectorization or custom instructions via our ACE tool. On the day of the hackathon, if you previously requested a cloud environment, you will be provided with an AWS machine that contains the following tools for the hackathon. From there, you can modify, rewrite, and experiment with your approaches to the Softmax function. From there, you can modify, rewrite, and experiment with your approaches to the Softmax function. And of course, we want you to have fun in this hackathon and hopefully walk away with something new. We look forward to working with everyone on the hackathon. Thank you.
Hi, my name is Kavyashree and I'm from India. And today I'm going to talk about my journey in this hackathon. I chose Andes project and I've been optimizing Softmax function for the past 4 days. So let us see, these are the optimization key areas given to us. I tried to experiment with all of these areas. So I used compiler directives for LLVM auto vectorization. I changed the code for exponential function into more fast Taylor series approximation and Horner series approximation. Both of them are polynomial approximation. And then I learned about intrinsic functions, and also I tried to implement more fast and efficient exponential function in a source file. So out of all the methods that I did, this method of LLVM auto vectorization as well as implementation of Taylor series by Taylor series and Horner series in pure C code gave me this good result. This result is from the Horner series implementation, and you can see the test count. For test 1 there is 3 samples, test 2 71 and test 3 2048 samples, as you know. And you can check that the cycle count has reduced to 2248, as well as the instruction count when compared to the raw pure C code, which is implemented using standard C library function, exponential function. And also you can see that it implements lot less, like around 1000 cycles lesser than the ACE implementation given to us. And then actually I also tried to implement the same approach in ACE source file, but since I didn't leverage the full potential of ACE, I couldn't actually get good results in that approach. So I think till today I've been doing this, and then this is the best approach that I got. And what I learned in this hackathon is that I learned quite a lot of things, even recording our own video for submission. And and you can see like I learned about the compilers, LLVM, how can we use them, how can we leverage them, and then I tried using I tried GDP debugger, and then I got familiarized with ACE Andesite, and then Andesite IDE, and then and also Copilot, and also I learned a lot of approximation methods for exponentials, and this journey of 4 days was very, very, very amazing and very insightful. I I hope I can I can get a lot from this. So thank you so much. I got a lot of learning in these 4 days. So thank you so much. Thank you for listening to my presentation.
Hello, I'm Marin, and this is my colleague Vincius. We're gonna present our project for hackathon. We chose Andes project, and we did acceleration of softmax algorithm using RISC-V vector extensions. So for this project, we did efficient softmax algorithm on Andes RISC processor. We'll leverage vector extensions for parallel computation, and we also use ACE, Andes custom extension, for tailored vector instructions. For this algorithm, we implemented 3 strategies. First, bit manipulation approximation. Second, polynomial approximation. And third, intrinsic function optimization.
Perfect. So starting with the exponential calculation, we have 2 strategies before. First is the exponential approximation, where the calculation really happens. For that, you have 3 approaches. There was the bit level approximation, the Taylor series expansion, and the integer fraction split, where the idea of integer fraction split is to split the value in the integer part, a fraction part. The integer part you calculate with the bit level approximation, and the fraction part you calculate with the Taylor series expansion. You also try a few range reduction methods, basically the logarithm one and the max value subtraction. The idea of the range reduction is to reduce the input data to a more stable range. Do the calculation in this range, and if necessary, you can reconstruct to the original range after. For this, you basically construct 2 types of algorithms, a bit level one and a polynomial one. You can see the accuracy of a polynomial one, that is the integer fraction split, is much greater than the accuracy of the bit level.
Performance-wise, we saw greatest increase in cycle counts for 16-bit length implementation. Smaller float size enable us to fit more elements into single register, which resulted in more parallel computation. Bit shrink also contributed to performance increase. For 64 bits to 16 bits, we had about 6 times performance increase, and from 64 to 32 bits, about 3 times performance increase. While 16-bit implementation had biggest performance increase, it took a significant hit to accuracy, about 50%, depending on algorithm. So for full results, you can see our full data for all our tests. The most accurate algorithm was with integer and fraction split, with a small decrease in performance over bit tricks, but accuracy gains. The best algorithm for performance to accuracy ratio is 16-bit polynomial, which had a great jump in performance and adequate level of accuracy. We also tested algorithm written only with intrinsic functions without using ACE, which saw a slight increase in performance and accuracy.
So for the conclusions, we want to talk about what we learned. Basically, we learn a lot about RISC-V, the RISC-V vector instructions. You see a great performance jump for machine learning workloads with using the vector instructions. You also learn about ACE, a copilot, that really helps to accelerate development, especially writing intrinsic functions in per C. We also learn about a lot more about the pipelines in RISC-V vector and the great performance improvements that it has. You also see that the 16-bit is a great match for machine learning workloads because it has a great throughput, which shows some penalty over accuracy. That's it. Thanks.
Thank you.
Hello everyone, and welcome to my presentation on the optimization of the Softmax function for the Andes processors. I'm Zain and I'm from VJTI Mumbai, and I live in Mumbai, India. I'm a student who's really excited about RISC-V and digital design, and this hackathon was an exciting opportunity for me to showcase my skills. Let's dive into my implementation. So, having a look at the starter code, it was apparent what approach I will be taking for optimization. The custom extension for the exponential function was quite rough, and I decided I can take two paths for the optimization. Firstly, being as I have a little bit of background in how residuals work and math, I decided to take an approach for improving the accuracy of the exponential function. And the second approach was a very common approach in which I decide to get a balance in the accuracy of the exponential function as well as the speed of the function. Let's dive into the first approach. So for the first approach, we can use a little bit of mathematical trickery to rewrite the exponential function as 2 raised to something, and we can split these two into two neat terms which are very easy to implement in hardware. So let's have a look at how we can do this. By the way, this is a very commonly used technique used in popular libraries like glibc for a very fast hardware implementation. So firstly, we shall decompose x into the following expression, and the neat part about this expression is that we have approximated n over here, and after using this x in our exp of x term, we can finally decompose it into two parts. Now the second part is neat because here r lies in the range of minus 0.5 ln of e to plus 0.5 ln of e. So we can use Esprin's scheme here to decompose this into a very neat polynomial. This is very easy to implement in hardware, and we finally come to the solution. So finally we use the Esprin solution and multiply it with 2 raised to n to get our final output. How to calculate the coefficients we described before for the Esprin scheme? We can use some software like MATLAB or Wolfram over here and use the 5th degree min-max approximation of the exponential function to get those coefficients. Finally, plugging them in together, we get the hardware implementation. You can see the results over here. I think I do pretty good in the signal to noise ratio, but there's a loss in the cycles because originally the template implementation takes about 800 cycles for the test 1 and test 2, and for the test 3 it takes about 5600 cycles. So of course there's a dent over here. Therefore I tried to come up with another approach which tried to balance accuracy with speed. Let's have a look at that. By the way, the disadvantages of using this method is a lot of DSPs will be used for the multiplication of the coefficient. So as we had a look before, the Esprin scheme, the polynomial which comes out, we'll have to multiply each of those terms with the input, which is quite expensive. So we'll have to mitigate them with good pipelining of the DSPs, as well as a neat hardware implementation of those DSPs. So for the second approach, I took up a very conventional lookup table approach, in which I implemented an interpolated lookup table, where using the lookup table gave me two advantages. First of all, the speed. So since I have pre-computed a lot of values and I have stored them into lookup tables, it is very efficient, and usually such tables also take up very liminal computational resources. And approximation, in which, because we have interpolated the answers from the lookup table, the answers won't be as accurate as the previous implementation, but they'll make do. So on the details of the LUT implementation, so I decided first of a maximum and minimum values which the LUT table could support, and I decided on the number of values which the LUT table will hold. This can be modified as per what approximation we are aiming to achieve, and what error rates we are aiming to achieve. So we can write a script for doing this. I personally wrote a Python script for generating this LUT. Finally, coming to the implementation of the LUT, the hardware implementation, we can implement the LUT as an file of ROM for minimal latency. Usually this can be done in 2 cycles. In my code, I've assumed latency for 2 cycles for the fetching of data from the LUT, and the interpolation logic is minimal and can be implemented as a combinational logic. No DSP is required. So all in all, this becomes a very efficient implementation. Finally, having a look at the results, you can see that the cycle count is quite close to the template implementations count, and we also get a good balance in the signal to noise ratio, while it is not as good as the previous implementation. So finally, of course, depending on the application, if it's like an MCU application, we can go with the LUT approach. If we're trying to make a floating point unit, we can go with the first approach, which will be much more accurate. All of the codes, again, I've put it in a GitHub gist for anyone to have a look, and it was really nice to have a look at the tools provided by the team at Andes, and it was a really nice setup for thinking and experimenting with the custom extensions, which is very interesting, by the way. So I had a lot of fun with that. Thank you guys, and hope you guys were satisfied with these implementations. Bye.
Hello everyone, we are Team RISC-V debuggers from SRM Institute of Science and Technology, Vadapalni campus, and we are excited to present our project on optimization Softmax computation for float 16 using RISC-V AC extensions. Softmax is a key operation in neural networks, especially in classification tasks. However, it's computationally intensive, especially in low resource environments like embedded system. Our motivation was to boost the performance of Softmax using hardware specific features of RISC-V architecture, namely RVV, vector extension, and ACE, Andes custom extension, while keeping accuracy intact. We also wanted to build a modular and reusable framework that could be extended to the other ML operations in the future. This project gave us a chance to bridge the gap between high-level ML concepts and low-level hardware optimization. Thank you.
To begin, we implemented a baseline C version of Softmax for float 16. This served as reference for both correctness and performance benchmarking. Next, we used RVV intrinsics to vectorize the operations. These intrinsics let us process multiple float 16 elements simultaneously, taking advantage of the SIMD capabilities of RISC-V. But we didn't stop here. We bought in ACE, Andes custom extension, a powerful feature specific to Andes course. These let us issue custom instruction optimized for float 16 math, which gave us a performance edge. One key part of our implementation was the manipulation of CSRs, control and status registers, to configure and monitor ACE behavior. We also worked with inline assembly for fine-grained control. Finally, we built a custom test harness to validate correctness and compute SNR, signal to noise ratio, which helped us confirm numerical stability of our vectorized implementation.
Now I'll be explaining you the several challenges we faced during the development process. Float 16 debugging was particularly tricky since it's not as well supported as Float 32 in most tool chains. We encountered compiler edge cases, especially with inline assembly and custom intrinsics. Understanding how to correctly set and interrupt ACE CSRs required deep dives into documentation and trial and error. But overcoming these made the results even more rewarding. Our final implementation using RISC-V plus ACE showed significant performance improved over the C baseline. We ensured accuracy with a custom verification routine verify buffer F16 with SNR validation, which confirmed our results were numerically stable. We also created a reusable infrastructure to test other float 16 vector operations in future projects. The project pushed our limits technically and gave us a exposure to both architecture level and application level design.
This project is innovative in two major ways. First, use of ACE and Softmax float 16 acceleration by student. This requires close interaction with the hardware abstraction layer. The combination of RVV and the ACE, we use a vectorization for throughput and custom extensions for raw speed, something usually seen only in production-grade embedded ML systems. The solution is impact efficient and designed for embedded deployment, making it ideal for real-world applications like tiny ML interactions on IoT boards, on-device language models, and smart assistants. As for future, we aim to extend this framework to other ML ops like ReLU, MatML, or layer norms. We want to explore dynamic workload distributions, optimizing execution paths based on profiling data in real time. And finally, we are considering contributions to open source RISC-V projects with our test frameworks and optimized outputs. Thank you, and we are open to questions.
Hello everyone, this is Team ASL Bravo and we are proud participants in the RISC-V Hackathon Online 2025. We are undergraduate students from Moymanching Engineering College, Bangladesh. For this hackathon, we took the Andes challenge, where our task was to implement a softmax function on Andes RISC-V vector processor with a focus on optimizing both accuracy and performance.
Let's jump into our solution. We are provided two implementations of Softmax, one in pure C++ and another one in also C++ with RISC-V vector intrinsics. We have optimized the vectorized implementation using several approaches, one of which includes avoiding redundant function calls, and we have also utilized the ACE custom instruction design tool, ACE Copilot, to generate the exponential function. The custom ACE instruction that was provided in the demo code used approximation techniques, which has very poor accuracy, but it is very fast in calculating the exponential. We have tried to keep the balance between accuracy and performance, and therefore we have used fifth order Taylor series to calculate the exponential. Our implementation comprises of 4 floating point multiplication, 4 fused multiplication and addition, and floating point addition, and 2 typecasts. In total, 11 floating point instructions. As a result, we can see that when the vector length is small, the signal to noise ratio is significantly high. But as the vector length increases, we see only a very marginal improvement in signal to noise ratio. But we observe a reduction in overall CPU cycle count and instruction count in all of the cases. In the Andes Clarity Pipeline Visualizer tool, we can see that there are very less pipeline stalls, and the exponential function completes in average 9 to 11 cycles, in all the cases, and there is subsequent generation of results in every pipeline stages. In the disassembly of the softmax function, we traced the custom instruction for the exponential calculation. The opcode was 0x4007b. We used the IPC viewer to find this instruction, and you can see the average IPC was 0.77. From the OPC viewer, we can see average OPC was 1.39, which indicates good vectorization of the custom instruction for exponential calculation.
In this challenge, our key observations are reduced instruction count by avoiding redundant function calls. The signal to noise ratio value was great for a small vector length. With the increase in vector length, the SNR drops. In all cases, overall CPU cycle and instruction count were reduced. IPC was 0.77 and OPC was 1.39, indicates good utilization of VPU. From this challenge, we have learned RISC-V as an open standard ISR, how vectorization is used in instruction level parallelism, implementation details of exponential function, Ace Copilot tool, Andes Clarity Pipeline Visualizer tool integrated with Andes Site IDE. Thanks to RISC-V International and Andes Technology for hosting this hackathon online. We have learned a lot, and we are very hopeful that the learning will be beneficial to us in our academic and engineering journey.
Hello everyone, my name is Tadej from Codasip. Our hackathon was all about accelerating the backend and the primitives of large language models, specifically the transformers encoder section of the whole LLM, which is an integral part of what you see in ChatGPT and similar products available right now. Here at Codasip, we strongly believe that software-hardware co-design is the way of the future, because the performance needed on platforms running that AI grows daily, and we must tackle that differently than how people are approaching it right now. And with our hackathon, we provided Codasip Studio, where the participants have taken some of our pre-written transformer code and then rewritten the software in their own way, optimizing it, then adding 2 new hardware instructions to the CPU that is running that code, and integrating both into a seamless flow of inferring the AI calls to achieve performance gains and optimization that cannot be done either by just optimizing the hardware or just optimizing the software. Thank you.
Hello everybody, my name is Tan and I'm going to present to you my results for the RISC-V Online Hackathon. So for this hackathon I managed to achieve a performance of 2079 cycles at the end, after all of my optimizations, and these are the instructions that I implemented. The first one I call multiply, shift, accumulate, the second one rescale, then saturate, add 2 times 16, saturate 16, and RELU. So multiply, shift, accumulate, it takes 3 registers and multiplies RS1 by RS2, shifts the result right by 8 bits, which is essentially converting a 32-bit fixed point number to a 16-bit fixed point number. And finally, it accumulates the result in DST. So I focused on this optimization first because it was in the hot loop for this function, which was in turn called in a loop by the main run transformer encoder function. Replacing the C code with this instruction only inside madvec-mu resulted in a dramatic improvement of almost 3x, dropping the cycles from the initial 30,000 to 12,000 cycles. And furthermore, this instruction could be used in other places in the code because the operation is fairly common, so later I'll show you how it further reduced the cycle count. The second instruction I implemented is called rescale, What it does is it first shifts RS1 left by 8 bits, then divides the result by RS2 and saturates the now result to I16 and then stores it in the destination register. So this is found in the hot loop for the fake softmax function. Basically, it converts RS1 to a 16-bit fixed point number and then divides it by RS2. The saturation is added just to shave off some extra cycles. So this led to another dramatic 2x performance improvement, dropping the cycles from 12,000 to about 5,000. Another instruction I implemented is called sat@2 × 16, which is a SIMD instruction. It splits RS1 and RS2 into two 16-bit ints each, and then adds the splits as vectors, saturates the results, and joins the results back into a single 32-bit integer in dest. So this took a lot of effort to implement, and it resulted in minor performance improvement of 5 to 10%. So I would say for this use case, actually, it was not really worth it, considering it. But maybe I didn't implement it the right way. In any case, let's move on to the next instruction, sat16. So this just saturates a 32-bit int from RS1 to a 16-bit value and stores that in DST. It ignores RS2, and it was the obvious place I should have started with, optimizing code by introducing instructions, because it's the first function from the provided template code. I added this instruction later in the process when I have already reached 2,500 cycles, and it further reduced it to about 2,200 cycles. The way I implemented this is by using arithmetized logic, so basically the branch 1 code times the condition flag plus the branch 2 code times the negated condition flag. This resulted in a modest but significant improvement of 10%, and if you wonder how I got to this 2,500 cycles before I reached this optimization, is by applying the first instruction I talked about, multiply, shift, accumulate, everywhere it could be applied. So that dropped the cycles from about 5,000 to 2,500, so another 2x improvement. And this is because this is just a very common instruction in this application code. The final instruction I try to implement is RELU, RELU, which performs the same operations as the saturated SIMD addition, but additionally trims the negatives results to 0. I failed to get it to work because I had some problems reading from the memory. I wasn't getting the data that I was expecting. So I tried to add some fancy instructions, but that didn't help. So I gave up on it. Maybe there is a correct way to implement this, but I didn't have high hopes for big performance gains because the SIMD instruction didn't help a lot, and that was used in multiple places. This RELU instruction is used in only one place, so I was not expecting more than a couple % improvement, so I left it at that. To summarize, I achieved about 15x performance improvement from the initial 30,000 cycles down to about 2,000 cycles, and even though my experience with Codasip is that it was still a little buggy and took a lot of time, it was slow, took a lot of reloads, it still grew on me as a powerful tool for hardware-software co-design, so this was a lot of fun. I hope to see you again soon.
Hello everyone, I am Soham Nutlikar, and along with my teammates Suman Zain and Dhruv Bhaib, we are third year Electronics and Telecommunication Engineering students from DSP College of Engineering in Mumbai, in India. Today we are excited to present our work on hardware optimization using LLM on a RISC-V machine. Through our custom hardware optimization, we successfully achieved 901 execution cycles with all test cases passing, demonstrating both speed and reliability of our approach. So let's get to it. How did we do this? The first instruction, hardware instruction A, was used in the HW_div function to handle integer division. Normally, this would require multiple instructions and branching, especially for divide by zero checks. By implementing this as a custom instruction, we handled all of that in hardware. No branching, few cycles, and faster execution. Our next instruction was instruction B, which performs a multiply shift add operation. We integrate this into the multiply function. This kind of operation is extremely common in linear algebra signal processing, when you're often multiplying vectors and matrices. So for us, introducing it directly into the hardware was a no-brainer. Although we aren't actively using instruction C in our implementation, we included that in the hardware since we had a free slot and the operation was straightforward. However, reviewing the final assembly, the output, we noticed that the compiler found it redundant and chose not to use it. While reading the hints, especially the part about Googling SIMD, we got inspired to think in terms of data parallelism that shaped the design of the instruction, as well as instruction F. Although we weren't entirely sure if it was parallel at the hardware level, it helped us save a significant number of cycles in practice. This instruction specifically handles multiply and accumulate operations, referencing values of a matrix and a vector. It processes by unpacking 4 units at a time, which mimics SIMD style behavior, makes it more and efficient than handling each element sequentially. We noticed the software saturation function used slow branching for range checks. By moving it to hardware with custom instruction E, we eliminated branches and made it run in a single cycle. While each operation sees small gains, they add up significantly in tight loops. During profiling, we discovered the vector addition loop was bottlenecked due to repeated loads, adds, and loop overheads in software. Our solution, the custom instruction F, streamlines this process, the entire operation in hardware. It takes 2 input arrays and an output address, then efficiently handles the parallel loads, instant additions, and stores while auto incrementing addresses. This eliminates instruction fetch, decode overhead, and branch penalties, delivering a speed up. This is perfect for acceleration, attention mechanism, and the other vector heavy loads. This hackathon really opened our eyes to the impact of the hardware level instructions that can have compared to the traditional software implementations. We learned firsthand how custom instructions can drastically reduce cycles, remove overhead, and optimize performance in ways that pure C code just can't imagine. We also explored the world of SIMD and realized how powerful this approach can be for processing large data sets efficiently. Designing instructions that operate on multiple elements in parallel gave us a deeper appreciation for hardware accelerated computing and the kind of performance gain it enables. Overall, this experience gave us a strong foundation in the synergy between hardware and software, and how thinking at both levels can help build a high performance systems. Thank you for the opportunity given to us. Thank you so much.
Hello everyone and welcome to our RISC-V Hackathon presentation for our team that's constituted of 2 people. My teammate Ines Menarbo Mazouza, who's a research intern at LAMI in France, and myself, Mohamed Islam Karabernou, who's a research assistant at NYUID based in France. And I'll be walking you through our presentation that we entitled When Software and Hardware Optimizations Meet, and I'll be guiding you through the totality of this presentation. So regarding our process, we first analyzed the software and hardware components, mainly analyzing the C code and the assembly of the original program. So from the software side, we noticed that there are some loop orders that result in redundant data accesses that can be avoided by changing the loop orders, and also redundant loops that can be fused. From the hardware side, we can see a lack of simple yet effective instructions such as the multiplication and division, and also lack of adequate support for fixed point data, incurring an overhead of requantization at the end of each operation. Starting with the software optimizations, we first applied a loop interchange at matvec_mul, where we can see that at each row in rows, the vec_c is accessed, hence redundant loads of this same data. In the modified version, we can see that after interchanging the loops going through calls and rows, we access vec_c only one time and then use it for all the necessary computations. So this optimization has an isolated impact of approximately 15%. And we also extended the use of this optimization by using the matvec function at single-head attention, where we can see the loop that using the dot product is equivalent to a matvec between q of I and the matrix K. So we replace that loop with the modvec function call, and the cumulated impact of these two optimizations is approximately 15.25%. The next software optimization is loop fusion at the feedforward function, where we can see that the modvec function already loops over ffdim, but we loop over it once again to add the bias. This is also noticed with the looping over model dim. So instead of calling the modvec function, we used its function body and fused the two loops that goes over ffdim, where in one loop we can first calculate the multiplications and also add the bias. The isolated impact of this optimization is approximately 13.7%. Another loop fusion is performed at the run transformer encoder, where we can see that the single head attention function already loops over sequence length and model dim, the same with the feedforward function. So what we did is that we added the residual addition inside of these two functions and send in directly post attention and final out tables to these two functions. So the cumulated impact of these software optimization is approximately 16.44%. Regarding hardware optimizations, we added the following instructions. First, multiplication, division, and also the saturate I16 first if statement and the second one. And also at the end, we added the multiplication with the shift included. So here we can see the isolated impact of each instruction. We can see that the multiplication that gave us the biggest impact, which is of 83.5%, followed by the accumulated impact of multiplication and multiplication with shift of 84.9%, and also we have performance gain when using the division and also the saturate if statements. So the overall cumulated impact of both software and hardware optimizations is approximately 93.05%, having a number of cycles of 2040. With this, we conclude our presentation. Thank you for following us and for this great opportunity that's full of learning and fun.
Hello, I'm Paulson from India. I work at Bosch as a senior OPD calibration engineer. I'm also an incoming MSCC student at NCSU. So the problem I have chosen for today is given by Codasip. I am aiming to accelerate the LLM primitives used in an encoder model. So the philosophy here is of compile, analyze, modify, and do over. So I have taken 3 steps for this particular problem statement. First is to identify the common operations that we're doing in this code. Then optimize the C code itself to remove any loops which can be clubbed together or collapsed into one statement or something. And optimize the whole resultant code for the given dimensions of the given problem statement. So for that, as a first step, I have added the profiler configuration into the Codasip IDE to get a sense of what are the hotspots in this code. So from that, I can understand that multiplication and division is something that RV32I is struggling with. So we had to add that. Second thing is we are trying to add custom instructions here. And in an example given by Codasip, we only have 5. So to make the use of the whole func3 space, we are going to extend it to 8 by using the configuration given in the model files that they have given. And third is the most important one of using SIMD or single instruction multiple data operations. So since we are working with S7.8, that is 16-bit data, we can have 2 of these into one 32-bit register, multiply it, do the processing, and get a resultant value in one single cycle. So effectively doing 2 operations in one cycle. So that will give us a higher throughput when we are doing the whole code. So going with the first step of identifying the common operations and collapsing them into a single cycle custom instructions, we have pack16 and max16x2. So we are packing 2 16-bit ints and then using max16x2 to multiply and accumulate the pairs. Shifting and saturation is done to fit the problem statement of having S7.8 operands. Then we have normalize to perform division and saturate the result. multiplication division hardware have been added through these instructions to the system. Next, we have ReLU for performing the ReLU function in a single cycle without branching. Then add and saturate to perform both operations in a single cycle. Then add, saturate, and ReLU to perform all three operations in a single cycle. So once we have implemented all these custom instructions, we have to optimize the C code itself. So first step is to reduce the calculations by pre-computing the row addresses while doing the matrix multiplications. Second, we can reduce loop overheads by replacing matrix to vector multiplications with matrix to matrix multiplications, so that we don't have the vector loop, the main loop all the time, and just have a 3-layer loop. Next, we can use a restrict keyword to make the compiler understand that a variable's pointer address will never change, so that it can optimize more aggressively. Similarly, we can typecast volatile variables to something else so that we can reduce the memory load operations, because the compiler will try to refresh the variable every time, and that will be a huge toll on the cycle count. So this is a result I've achieved. With the original code, we had a cycle count of 29360. With custom instructions only, we have gone down to 2252. And further code optimization has brought it down to 1799. And finally, using a brute force method of unrolling all the loops for the given dimensions, just removing all the loop counters, we have come down to 1494, giving us a speed up factor of 19.651. So looking at the profiler output for the instructions used, we can see pack16, max16x2 used for multiplications. Add saturate has been used for calculating the residuals. Add saturate ReLU has been used for calculating the hidden layer in the feed-forward network. ReLU and normalize have been used for the single head attention block function. So as a further possible improvement, I thought we could use funct7 bits to encode a way to use continuous sets of registers to have more pairs of int16, so that we can do more parallel multiplication and have a better throughput. Secondly, we can focus on matrix to matrix multiplication instead of matrix to vector, because it has less loop counters, less loop overhead, and generally is a simpler code design. So yeah, with a factor of 19.651, that was my result. Thanks for listening.
Hey guys, I'm Atman, and I have with me Aditya, and we both are digital design engineers at Texas Instrument Bangalore, and we'll be going over our work in this hackathon. So what we'll be showing is our how we've achieved sub 1K cycles. We've achieved a number of cycles of 965, so that's coming down from close to 30K cycles. So it's about a 30x performance improvement. And mainly we've done this using two major approaches. One is by using multiple SIMD instructions, or single instruction multiple data. That's on the hardware side, and the other side is kind of using it intelligently in software and calling it intelligently in software, and also basic like good practices in code and profiling your code. So yeah, so what our approach is that we try to pack in as many SIMD instructions as we can, and what we notice as the major bottlenecks in the code is that we have 16-bit of fixed point data, but our RISC-32 is capable of fetching or loading and storing 32 bits at a time. So why not we create custom, like since we have registers 32-bit wide, why can't we just load in two 16-bit values at a time? So the idea is kind of, I'll just explain one. For example, a dot product between two arrays. We do a single load word where we load in 32 bits, which contains two 16 bits of data. Then we multiply those 16 bits of data in hardware. We scale it by 8 bits because there's 8 bits of mantissa. And you want to scale it back to S78. And then you add it and you get your final dot out. And you can also accumulate it over the previous register. So that way you get an accumulation kind of instruction. So this will be useful when you want to implement like a weight or like an array into another array, a dot product between two arrays. So similarly, another bottleneck is if you want to see in the scale and normalize function where you have an array and you want to normalize the entire array by dividing it by sum and multiplying it by 256. So in the same way, you can read in 32 bits at a time and split them up, scale them, divide them in parallel, saturate them, and then just concatenate them and write it out as one 32-bit word. So that way you're gaining 2x performance. So similarly for the add and saturate, so these are instructions where you can add two arrays in parallel at a time. And similarly for the ReLU, so for ReLU we have two locations where it's being used. One is where you read in two samples and you just compute the ReLU on both of them. And another one is where you keep accumulating the ReLU. So we've developed an instruction where you can actually provide it as a muxed input, where you either just give the concatenated output 32 bits or you can sum it and accumulate it with the previous. So yeah, moving on to the software optimizations. Aditya.
Yeah, as Arvind mentioned for the hardware, by using the SIMD instructions, we basically half the loop counts wherever the SIMD instructions are now getting called, which leads to the biggest cut in cycle time. We also did some major software improvements in terms of removing if statements and conditional branchings wherever possible, especially in loops. We also reduced memory loads wherever possible by retrieving two 16 bits of data at a time by typecasting the value to a 32-bit data. We also generalized the hardware instructions to allow for repurposing and clubbing together different steps. So for example, in the first picture that you see here in the dot product, we're able to club both the matrix multiplication and the addition of bias into one single instruction. And we later reuse this multiplication plus bias instruction in another place in the code by adding zero in the bias part, thereby just doing a matrix multiplication. This allows us to save even more software cycles. And after this, we came down to around 1,200-ish cycles. We needed to perform several like minor hyper optimizations to cut it down to a sub 1,000 goal. So we did things like using static functions to cut down on a lot of code overhead to boost the performance. We used in several hardware instructions the accumulate function to allow for reduced variable assignments and reuse the same variable again and again for accumulation. We use bitwise operators wherever possible. For example, on the right side, you can see on the bottom part of the code, we use a bitwise operation to get the last bit out instead of using a modulo. This allows us to save on cycle time. And we also did tiny things like using this built-in expect functions to cut down on the branch prediction overhead that's caused when we are executing our code. So ultimately, what we realized and what we learned the most through this project is that optimizing the CPU performance and creating these hardware instructions is extremely use case dependent, and there's no one shoe fits all size policy. So we really learned a lot in terms of creating custom hardware instructions and analyzing the problem through different lenses to really hasten up the cycle time. And that's it. Thank you for listening to the presentation.
Thank you.